share my screen in such a way that I could see you all a bit as well, but apparently not. And I also can't see where I am either, so I might, if I like disappear off the side of the camera or something, then give me a shout. Yeah, so I started at Queen Mary just at the end of 2019. I joined as a Royal Society Research Fellow, so that means that I sort of bought a chunk of money to fund my research on this kind of topic that I'm going to discuss today. And with that, I sort of also leveraged having a permanent job at the end. So I'm doing some lecturing as well, and in return, when my fellowship ends, I'll be here permanently at Queen Mary. So yeah. I won't be able to see questions as we go, but there should be some time for some at the end. But if you have any burning questions or anything, then feel free to speak up, I guess, as we go. So actually, one quick question. Can you see my cursor? Can anyone see where I'm pointing at things?
Yes, yeah. Can see your
Excellent, brilliant. Okay, yeah, so this talk is going to be sort of looking at things on the scales of star formation. And how clusters of stars are born, right down through to how planets are born, and how these things all link together. So we're looking at maybe planets in the context of this bigger picture. Now, I actually gave a talk for SciStar about 8 months ago, focusing on some of this stuff. And so, because I don't want to repeat myself too much today, what I'm actually going to do is give about half of a talk, which is fairly well known in a sense. I've given it this sort of first half quite a few times. It should be reasonably well polished. And then in the second half, what I want to do is focus on actually not what I'm doing, but what my colleagues working with me are doing at Queen Mary. So I'll be discussing some of the work that Julia is doing, who's a postdoc working with me. There's Lynn, who's a PhD student who just started in January. Kanar, who's a third-year undergraduate doing a research project with me, and Susanna, who worked with me last summer as well. So yeah, half the talk will be sort of framing the problem and why we're interested in it. And then the latter half, I'm going to list some problems that are still outstanding that we haven't solved yet, and what these people are doing to try and address those. I should just point out that it's purely coincidental that these are all women or females. I've not selected these specially. It just happens that that's the nature of the team that I'm working with, which is great. So yeah, let's start at the bottom end, at the smaller scales. So exoplanets. So in the last 5-10 years, the number of planets that we've found around stars other than the sun has really dramatically increased. And so we have something now like 4,500 planets confirmed. And they're also really, really broad in their properties. So some of that diversity in the planet properties is illustrated here, where I'm showing the planet orbital period on the x-axis. So that's how long its year is. And this is essentially a proxy for how far away the planet is from the star. Okay, a short year is a close-in planet, long is far away. And just for reference, here is Mercury, the Earth, Jupiter, and Neptune, I think that is, or Uranus, doesn't really matter which. And then on the y-axis, we've got the planet mass in terms of Jupiter masses. Now, this dotted line is the limit of our observational capabilities. So beneath this line, we just can't really see planets yet because our telescopes aren't good enough, or we've not been looking for long enough. But above that line, there's I've heard this referred to as a shotgun blast in the distribution of planets. They're just everywhere. We've got these hot Jupiters that are massive planets that are close to their parent star. As you go down here in mass, the atmosphere can actually just get completely burned off from these planets, which is maybe the reason that there's nothing here. But then down here, you end up with rocky sort of lava worlds, which don't really have an atmosphere, which is why they're low mass, but their surfaces are probably molten. Then further out, as things get cooler, we find rocky planets, perhaps a bit like the Earth. But the Earth is actually sitting here where we can't really find things. So typically you're finding what we call super Earths that are a bit like the Earth, but more massive. You then have ocean worlds and ice giants, and then, of course, the cold Jupiters too. So, there's a great big diversity in the properties of these planets. There's also diversity in the numbers of planets per star. There's diversity in the types of planets you get for stars of different masses. It varies also with the things like the star's metallicity. So, there's a great big range of planetary properties that we're now finding, and we want to understand them. And to achieve that, we have to do two things. One is understand how the planets form in the first place, and the other is then understand how they subsequently evolve. And it's the planet formation that I'm mostly interested in. So how do planets form? Well, if you look at our solar system, the planets are all going around the sun in a flat plane. So, you know, none are going sort of over the top of the sun. And they're also all orbiting the sun in the same direction. So when we then go and look at young stars in star-forming regions and see that they're surrounded by flattened sort of dark silhouettes here, these are the natural place to think that the planet formation might be happening. So we call these protoplanetary disks. So here we've got a face-on example. So you're able to see the star because the disk is around it. It's like a donut. And then there's one here that's edge on where the disk is blocking out the star's light. And through the Doppler effect, we can actually see that these disks are rotating. So, you know, we have pretty strong evidence that this is where planets are born. Now, these were observations with the Hubble Space Telescope back in the mid-90s, but our view has improved since the 90s. These are recent observations with something called ALMA, the Atacama Large Millimeter Array. And ALMA can look deep within these disks, and so you can see that our view has dramatically changed. So here's just a gallery of observations of disks from recent years. And one thing in particular you'll notice is that if I jump back, this view that we had before of like a smooth disk is completely gone. You know, we're seeing these concentric rings of bright and dark regions. And, you know, when this image was released back in 2015, it caused a bit of a revolution, right? These signatures in this disk might well be due to a planet or many planets in there sort of carving out these features. It's important to note that these observations on this slide of these planet-forming disks are all of what we call dust in astrophysics. So that is basically just small solid particles, a bit like a grain of sand. And specifically, these are all observations of dust that's about a millimeter in size. And the reason that's quite important is the dust can be sort of shepherded into these rings a bit more easily than gas. So the gas here might be quite smooth still, but you know, the dust, it now seems that if you look at the dust in a disk, it has always got some sort of substructure to it, which maybe is due to planets. And a huge part of the planet formation community is now looking at these kind of observations and asking the question, can we go from these disks and these fantastic new images we're getting in the last 5 years and understand how this links to planet formation, and can we use this to predict the various exoplanet sort of architectures that you can get. So this is what a lot of people are doing, is trying to go from these sort of observations to this sort of populations. But I'm going to ask throughout this talk whether or not we can really do that with these disks, because I'll discuss this a bit more later. These are all relatively close by disks to the sun, because that means it's easier to observe them. They'll look a bit brighter if they're closer, and also you can resolve these features more easily. So I'm going to ask the question throughout this talk: can we go from these disks to the exoplanets? So let's, in asking that question, sort of look at a bit of the context of where these disks are found, and how long do they live for. As we'll see in just a second, stars normally form in very big groups of up to like hundreds of thousands of stars together. And so if you want to get an estimate of how long the disks live for, what you can do is look at star-forming clusters of different ages and count the fraction of stars in them that actually have these disks. So that's what's done here. Each of these coloured points are a different cluster of young stars. And on the x-axis here, we're showing the cluster's ages in millions of years. And then what we've done here is looked at the cluster and counted how many of the stars have these disks. And so early on, at about 1 million years, most of the stars still have a planet-forming disk. But then by about a few million years, most of them are gone. Okay, so that's sort of our typical time scale to make planets, has to be within a few million years. And I know these timescales sort of get very abstract for us. They're not very human timescales, but 3 million years isn't very long for a star. So the planets are made very early on. And when you're in these star-forming clusters, this is what the region will sort of look like. This is the Eagle Nebula. And what you have here is some young stars sort of centrally located here. I mean, there's young stars throughout the region, but most of them are in here. And you have these pillars pointing towards those young stars. And then there's this great big blue bubble, whatever that is. And then there's sort of more gas around the edge that's a different color. So what's going on? Why does a star-forming region look like this? Okay. So what I'm going to show here are two computer simulations by a guy called Jim Dale. They're going to be a spherical turbulent cloud that's going to collapse under gravity. So this computer simulation describes how fluids move around. It describes gravity. And what you'll see over time is that these simulations, can I pause it? No, I can't. Will collapse under gravity and start producing filaments. So these long sort of chains of material, and those filaments are really good at funneling material down onto the stars. So you've got a young star cluster forming here on the left. Now the simulation on the right you're probably looking at now is behaving very differently to this one on the left. So what's the difference there? What extra ingredient does this one have compared to this one? Well, they are exactly the same initial conditions, these two models. But in the right, what is being included is a recipe for how high energy light from stars can break apart atoms, can ionize them. Okay, so if you get a photon that has an energy of more than 13.6 electron volts, if that gets absorbed by a hydrogen atom, that hydrogen atom will lose an electron. Okay, and because you've absorbed that photon's energy, the resulting two particles that you have, your proton and electron, they have more kinetic energy than they did before they absorbed that photon. So what is temperature? Well, it's just to do with the kinetic energy of the particles. So when you account for that ionizing radiation, you heat the gas up a lot. Okay, so the stuff in here in this bubble is 10,000 Kelvin because of that ionizing radiation, whereas the stuff out here is only about 10 Kelvin. So that's what gives you the difference. Okay, if you don't account for this high energy radiation from stars, the gas all just sits in there with the young cluster and keeps feeding it and making more and more stars. But then if you have massive stars, they can heat up the surroundings by ionizing the gas, and you blow these bubbles. And interestingly, those pillars, which we saw on the previous image, like the pillars of creation, are actually the leftovers of these accretion flows. They're just pretty dense, so they live for a bit longer. So you can look at something like the Eagle Nebula now and hopefully have a picture of what might have happened to form this, right? You had a turbulent cloud collapsing, and these probably were filaments that were channeling material down into this young star cluster. And then this bubble exists because there's massive stars in here that emit a lot of this high energy light that is ionizing the gas, making it really hot. And then these are just leftovers of the stuff that was channeling material down to the young stars. So this is a star-forming region, and this is roughly how it evolves. So how does this all link together? We've looked at a whole bunch of different ingredients so far. You're probably feeling a bit lost. Well, let's look at the different ingredients we have side by side now. Okay, so we have these simulations of a star-forming region over time, and we have these observations that tell us if we look at a cluster of a certain age, how many stars have disks. So this is that simulation after 1 million years. So if we were to go in here and count the stars with disks in a real system that was like this, somewhere between 60 and 80% of the stars would have disks. And then as we advance through the simulation, that fraction of stars with disks drops off quite sharply. And by the end, more than half the disks are gone. Okay, so this doesn't look like a very long period of time for the star cluster, right? Not much has really happened, right? For stars, this is really young. But actually, the entire story of planet formation has to have happened over just these few frames, okay? So the important takeaway point really here is that if you're making planets in these disks, you're doing it generally in this kind of environment, okay? It's not, the images I showed you before, you can imagine those as isolated systems just sitting out there in space, those disks, but actually they're in this kind of region typically. So how can a star cluster, where you're making your young stars, actually affect the disks and affect the planet formation? Well, one way is through gravitational interaction. So this is an extreme example called RW Auriga. This is an observation of what the system looks like. So you've got two stars with disks and then this ginormous tail and also all this mess over here. And here's a computer simulation of what we think is happening there. So this little star here is going to fly past this star with a disk, actually steal some disk material and induce this great big tidal tail. And the impact of that is really huge. It shrinks this disk. It makes loads of material jump onto the star, which launches a powerful jet that we see. So, you know, this is potentially quite significantly influencing your planet formation in this disk. Now, it turns out these kind of interactions, these close encounters are quite rare. But even for a larger number of stars in a cluster, you can still have interactions between them and their disks that you know, are more subtle, that don't do as much. So this was some work by Giovanni Rizzotti looking at clusters of stars with disks and trying to see, you know, how their gravitational interaction through more distant encounters affects the disks. And a little bit later on, I'll look at how you know, how important this is. So that's one way that the cluster can affect the disks, is just through gravitationally perturbing the disks. The other way, which is the one that I'm mostly interested in, is called external photoevaporation. So that is, you know, we just saw in that simulation of the star cluster that the radiation from the massive stars can blow that hot bubble and disperse that star-forming gas. Well, radiation can also heat up disks and drive material from them. So here we have a artist's impression of a star over here shining on this disk, and maybe you can see that there's a sort of a wind being driven from it. So you know, what can this do to the disk? And let's have a look. So we have direct observations of disks being affected by radiation. So, you know, so we can actually see it happening in action. We don't just have these artist impressions. But it behaves potentially very differently depending on how strong that ultraviolet radiation is that's shining on the disk. So what we have here is a sort of a cartoon, I guess, of how strong the UV radiation is. And it's in funny units called G0, which you won't have come across before. But for reference, a value of 1 is just sort of how strong the average radiation, UV radiation field is in the solar neighborhood. So, you know, near the sun, and it's low. Okay, this is just a low value. If you go and look in the middle of the Orion Nebula cluster, where there's loads of massive stars, so it's about 100,000 times stronger a UV environment, then we've been able to see disks getting evaporated for decades by this radiation. So this is back in the 90s again with Hubble. And you can see they no longer really look like disks. In this example here, you can sort of see the dark silhouette. But you've also got all this cometary plume of material coming off the disk. And that's just because this thing's being shredded so quickly by the radiation that, you know, so much material is coming off, you know, that it's kicking it all out like this. And these, so we call these proplids, these systems, and they typically point towards whatever star is evaporating them. And so this is all we had for a couple of decades. And because these proplids are actually fairly uncommon, most stars are not going to be subjected to something like this. People sort of ignored the effect of this external photoevaporation on disks and planet formation. But about 5 years ago now, Serena Kim at the University of Arizona found proplid-like objects in a UV radiation field that's like 100 times weaker than in Orion. And then in 2017, I found evidence for a disk evaporating in a really, really weak environment. And the reason this can happen in this situation is this disk is just so big that the outer parts of it are not really very tightly bound to the star. The gravitational pull is weak. So you only need to warm it up a little bit in those outer regions and it can start to lose material. But this is the only example we really have down here. And then in the middle, in this sort of intermediate regime, we have no idea what to look for, because it probably shouldn't look like a proplid, but you know, we don't know what to look for to find evaporation here. And that's something I'll be addressing a bit later. But we can indirectly also search for evidence that the radiation is affecting these disks. So this is a direct observation. You know, we're saying, here's a disk, oh yes, it's being evaporated, and here's another one, yes, it's being evaporated. But we can also take a statistical approach to see what the radiation might be doing to the disks. So this was some nice work by Megan Ansdell back in 2017, looking at a star cluster called Sigma Orionis. And there's a massive star here, which emits a lot of this UV light at this position of this white cross. And then there's all these other stars, many of which have disks in the sort of the vicinity of it. And what Megan has done here is plotted how massive the disks are as you get further and further away from this massive star. Okay, so this is projected separation from that star, and this is how massive the disks are. And you can see that they get more and more massive as you get further away. Now, this isn't conclusive, but this suggests that if you put a disk near to the strong radiation field, then that disk mass gets lowered. Okay, so we think disk masses get lower if you put them in these harsh radiation environments, which could affect maybe your planet formation. If you have less material to make planets, then that might affect the kind of planets you can get. Another sort of statistical study was this one, where they looked at something called the Cygnus Ob2 Association, which has a bunch of massive stars that emit this harsh UV light. And there what they did was break the region down into sort of regions of different radiation strength. So that's what's on the x-axis here. So over here is strong, and over here is a bit weaker. And again, they've in these little sub-regions of this cluster, they've counted the fraction of stars with disks. And because this is all one cluster, all these stars should be a fairly similar age. So what you're seeing here is that although these have similar ages, in the stronger radiation parts, less of the stars have disks. So this is evidence that if you're in a harsh radiation environment, disks live for less time. So we have evidence that the masses are affected, that the lifetimes are affected. And then this is a really horrible plot. I apologize in advance, but I'll summarize it with a cartoon next. So this is showing disk sizes on the x-axis, and then what these different colored lines are distributions of disk sizes in different star forming regions. So what's important here to take away is that this purple line is the Taurus star forming region. This greeny, cyany, teal one is Lupus, which is another star forming region. And then this red one is the Orion Nebula cluster. Now, the red, green, and purple all have the same age, but the red one is systematically smaller, right? These ones have disks that are hundreds of AU in size sometimes, and typically many tens of AU. But the Orion Nebula cluster disks are much smaller, typically only 10 to 20 AU, never getting up to 100. So what's the difference? That's the question. And the answer is that this one has massive stars in, and these ones don't. So it's the radiation again. So the sort of conceptual summary to take away from those fairly dense slides we've just been through is that if you shine this UV light on a disk, you expect that it will lower the mass of the disk. You expect that it will shrink the disk size, making it smaller, and you expect that it reduces the lifetime. And our initial motivation here was, why are exoplanets so diverse? Well, maybe the answer is there's a big diversity in the environments that these disks are trying to make their planets in. A sort of nature versus nurture argument. So if you have more mass, you can make more planets. If you have a smaller disk, then that doesn't allow you to make planets out here, perhaps, and so on and so forth. So this is really what I'm focusing most of my attention on in my research. So I've mentioned two processes in clusters that can affect the disks. One is gravity, so a star flies by and affects the disk, and the other one is radiation. So which one's more important? Well, Andrew Winter had a nice paper comparing the two processes. So what he's showing here, again, is a fairly complicated plot. The x-axis is how many stars there are in a box that's a parsec size. How many stars per cubic parsec? So this is lots of stars, this is not very many. And then the y-axis is how strong the radiation field is, so weak and strong. And then these coloured regions are real star clusters. So you can see that the most stars are sort of in this along this line here. And then the right-hand panel is exactly the same, but he has run models using that account for the gravitational interactions of how the disks are affected, and also using some stuff that I've done accounting for the evaporation of the disks. And if you lie above this line here, then the radiation destroys the disks really quickly within a few million years. And if you're to the right of this line, then the gravity will destroy the gravitational encounters will destroy the disk within a few million years. And then up here, they're both important. So the takeaway message from this is the real star clusters mostly sit where radiation wins. So typically the gravitational encounters aren't as important we expect. I'm nearly done with this sort of initial motivation. I just wanted to highlight this recent work from Andrew Winter again. So this was really cool because most of the attention has been spent looking at how the disks are affected by radiation. But Andrew has been the first one to make a link to how the planets might actually be affected by their environment. So what he's done is there is a telescope called Gaia in space, and we're going to talk about this more in a second, which has mapped very accurately the 3D positions of stars, so we know where they are and how far away, and also their velocities. And so what Andrew did was looked for stars that are sort of in clusters in this Gaia phase space of positions and velocities, and compare those with stars that are sort of sitting on their own. And he's asked, well, do their planets differ? So here we have two plots that are the same axes. So how far away a planet is from its star and how massive the planet is. And the blue panel here is stars that are on their own. They're not in a cluster. And then the red is stars that are in clusters. It's in these Gaia sort of overdensities. And the interesting thing he pointed out was you have an overabundance of these hot Jupiter planets when you're in a cluster. So it might not have happened that this might not have been set up when the planets were actually formed in the disk. It could have happened later on because these are quite old systems that have been clustered together for quite a long time. But we now, just in the last 6 months or so, are getting evidence that the planets themselves care about where they were born. So yeah, I was saying earlier on, for the first half of the talk, I want to ask the question, can we make this jump from these nice observations of disks to the exoplanets we're seeing? And I mentioned that these disks are unusual. They're very close to the sun. And we focus on those because they're brighter and it's easier to resolve their substructures. If I hold my fingers up and get further and further away, eventually you can't tell that they're separated because you can't resolve the separation. So it's the same thing here, right? We're looking at close by disks because you can see these features easily. And it turns out that the radiation these kind of disks see is unusually weak. Okay. So this is yet again Andrew Winter. He's done loads of work on this stuff in recent years. Again, how many stars you have in a cubic parsec and how strong the radiation is. But now we're sort of saying if you took any random star, in what kind of environment should it have been born? And so dark stuff here is very probable, or most probable, and the sort of whiter light grey stuff is least probable. And people would normally previously ignore the role of environment because these things are rare, and that's true. These proplyds that are getting absolutely zapped. But these things we're also focusing our attention on now are also rare. Most stars form in this sort of band, and there we're not really looking at very much at the minute. So this is going to be important. So yeah, that's sort of the takeaway message of the first half of the talk is planets form in these disks, and those disks are only found around young stars, and the young stars are in these clusters, and the clusters can affect the disks. And these things that we are focusing on are sort of not typical, which could be a problem. So I said I didn't want to labor too much what I've been doing and focus on the people working with me. So I'm just going to mention in passing that my main contribution to this is working on computer simulations of evaporating disks. So here's one of my models. So you've got the disk down here and a wind being driven off of it. And in particular, one thing I've done is develop a grid called fried, which, if you have a star of a certain mass with a disk of a certain size and mass, and you shine a certain amount of UV light on it, this will tell you the rate at which that disk will lose material. So, all Andrew Winter's stuff, this and this stuff, asking what's important, uses fried. So this has really opened up, because this is quite a hard thing to model, it turns out. And by providing this to the community, it's really opened it up as a problem that lots of people can start thinking about. So yeah, since about 2016, I've been working on this problem quite a bit. But yeah, what are some outstanding problems regarding how environment affects disks, in particular in terms of how the radiation affects disks? So one is we need to really understand the true distribution of environments that disks are exposed to. So, what fraction of disks see a weak UV environment and what fraction see the very strong ones. So everything I've shown you so far was, in that regard, is theoretical. So we had this stuff from Andrew Winter. This distribution is theoretical. It's saying these are relatively rare and these are relatively rare, but is that true? So we need to ideally observe this kind of distribution directly. So that's problem number one. Problem number two is with regard to directly observing these evaporating disks in the sort of intermediate environment. So, I showed you this plot earlier on where you've got how strong the radiation is. So weak, strong. Yes, here it's easy to see the evaporating disks. Here it's a little bit harder. Here we have one example. But really, we generally don't know what to look for down here to find evaporation. So, if we don't know what to look for, then we're not going to find it. So we need predictions of what you should see here. That's problem number two. Problem number three is a bit vague. I'm saying, how do disks actually evolve in star-forming clusters? So typically, when we're modeling a disk being shone upon and evaporated, we just say, oh, it starts off as a certain size and we're going to shine a constant amount of UV radiation on it and just see what happens to it. But that's not really quite true, because stars form at different times in the cluster. They form sometimes embedded in gas, they move around, so that the environment they feel will actually change over time. And so far, that's not really been properly accounted for. And then the big question, does planet formation actually care? If you evaporate a disk, does it actually matter, or do the planets just form and not really care about what that's doing? So those are sort of four big problems that I'm interested in at the minute. So let's look at the first one, the true distribution of environments that disks are exposed to. So this is what Susanna was working on last summer with me, and as an RAS funded summer student. I didn't really emphasize this earlier, but if you're interested, then summer studentships are great. Often, well, they should be paid. There's usually ways of getting funding. If you are interested in a Royal Astronomical Society funded one, which is what Susanna had, you really need to contact someone before Christmas, because the deadline is sometime in January to apply. So I'd encourage people to think about summer studentships, because they're really good. You sort of get to join the research group and get experience of what it's like to be part of one. So mapping the UV environment. So this is just another example of a star forming region. We've got a bunch of massive stars here emitting harsh UV light. And we want to be able to say, this star over here has a disk. What UV field is it being exposed to? How strong is the UV radiation that's trying to evaporate it? And that's quite hard to work out. It's even harder, actually, if you're in quite a low mass star forming region like Taurus. This is the one where we're getting all those nice images of disks, because here no one star dominates that UV radiation. The UV field that this star sees and its disk is getting affected by could be combined effect of all these stars here. So how can we go about estimating this? So Susanna's job was to look into using Gaia, which I already mentioned, works out accurate 3D distances. Here's just a quick video sort of illustrating some results from Gaia. So here we have the sun. It will get fainter in a second. And then what the video is going to do is zoom out. And, it's like in Star Trek or something when they're flying through space and you've got the stars going past. But these are actually accurate 3D distances to the stars as determined by Gaia. So this is cool because it means, this star receding off there, let's say we're interested in what that feels, we can now get the 3D distribution of stars around it. Okay, so we can get proper 3D star maps now. So for this problem of understanding how strong the UV radiation is anywhere, you could hopefully use Gaia to find the nearest stars to your disk and work out how their radiation will combine to give the UV field at that disk. I've not explained that very well. As I said, this sort of latter half is rigged up quite quickly, but hopefully this illustration will make it a bit clearer. So let's say we've got a star at this position here, and we want to know how it's being irradiated, because we want to understand how that affects its disk. Well, with Gaia, you can say, well, let's search the surrounding 3D space, not just 2D on the sky, and find the nearest N sources that have strong, relatively strong UV fields. And then you can say, well, their combined effect, you can dilute their radiation and sort of work out what their combined effect is at that point in space. So Susanna, I mean, my goal for the summer project was to roughly understand how you can query Gaia data and how we could maybe use it for this problem. But this is actually from her project, and she had this working prototype. This is real stars, not fake data or anything. And so this tool is essentially there and ready to be used now. But there is a problem still, actually, which is that estimating the actual amount of UV light that these stars emit is quite hard. And another problem is there could be dust and gas in the way that blocks out some of that UV light. So I just wanted to mention briefly on this sort of whirlwind tour of research at Queen Mary that one of the things I'm doing recently is working on a new space telescope called Hyperion, or at least a proposal for a space telescope, which would be able to actually tell us what the UV radiation field is from all those stars, and also potentially directly just measure it at the disks as well. So this is quite an exciting new thing that could help here. So understanding the distribution of environments, we've got this sort of 3D mapping tool that Susanna's produced, and also Hyperion, which can help with that too, coming up in the near future. But we still don't have this solved. Number two, observing this evaporation in sort of this intermediate and weak UV environment. So how can we do that? Unfortunately, the signatures that we're coming up with are fairly complicated to explain, but I'm going to try and do my best to just sort of illustrate the main gist. So here we have a model of a disk, and you can imagine that it's spinning around like this. And so if you were looking at this, the material on this side is going to be Doppler shifted so that it looks more blue. It's coming towards us, and this side is going to be Doppler shifted to be more red. So if you scan from left to right across this image and plot how fast stuff is going, you get something called a position velocity diagram. So this is scanning from left to right, and the y-axis is showing you how fast stuff is moving. Now for a rotating disk, just the most basic description of how fast it's going, a certain distance from the star is given by, it's called Keplerian rotation. And so in this kind of plot, if a disk is just spinning there and being very boring, the takeaway message is that you should get a picture like this, with no emission here, and all of the emissions should be sort of contained within this curve, which is described by this equation. And you have the same curve on the other side. So what I did was, it turns out that if you use like our most common tracers that we observe disks with, to look at that Doppler effect, you do just get that boring sort of signature. But if you take a disk model where it's evaporating and look at something like atomic carbon, so often we look at disks with carbon monoxide that probes the disk quite well. But as you get out here into this evaporating wind, that carbon and oxygen molecule gets, the CO molecule gets broken up. So it therefore makes sense to try and look at just the atomic carbon, the atoms that are left over after that molecule breaks up. And if you do that, that plot from the previous slide looks very different. Okay, so just comparing them, you get emission that is faster than you'd expect from a disk just rotating, due to Kepler's laws. And you get emission from these quadrants that isn't there in these sort of just a normal disk. So as I said, this is complicated. You don't need to worry too much about it. The important thing is that we expect that atomic carbon in this wind is a good tracer of evaporation. in these sort of environments. So maybe that's what we need to go and look for. And we can look for this with ALMA, actually. So I'm in the process of writing ALMA proposals to try and do this. ALMA, please give us the time. We'd really like to fill in that gap of directly observing these evaporating disks. Unfortunately, ALMA is very competitive. It's got something like a 1 in 10 acceptance rate for proposals, so the odds are not with me. Julia, a postdoc working with me since October, is looking at other tracers. So one is oxygen 1, which is really good for analysing internal disk wind. So that's where the parent star shines on the disk and drives material from it. And normally what you'd expect to see, if you just look at how bright the emission is from this evaporating disk at different speeds, is you'd have blue shifted emission from the sort of top surface coming towards my eye up here, and then the stuff down here is red shifted from the disk. So because the red shifted stuff has to go through the disk to get to my eye, where there's lots of dense material, we typically expect the red side to be fainter than the blue side. You know, this stuff just goes straight to my eye. This stuff has to go through the disk first, so it gets fainter. So Julia was asking, I should point out that this sort of blue asymmetry then is the typical, is a characteristic signature of a wind. So Julia was extending this to look at, well, what happens if you have an external wind too, which typically moves material from the outer disk. And it turns out that it's not very good, actually, for this sort of unresolved approach, you know, where you're just looking at how bright things are at different speeds. And that's because this wind has to be driven very fast, but this wind can be driven quite slow. And the reason for that is, you know, you all hopefully have come across the idea of escape velocity. If you try and launch a rocket from the surface of the Earth, you've got to give it a real big kick. But if it's already sitting near the top of the atmosphere, then you know, that kick can be much smaller and it can escape. So that's just what's happening here. This material is really close to the star, so you need to make it fly away very fast. This material out here is far away, so you just give it a little nudge and it can slowly drift away. So unfortunately, this red line here is what you have for the internal wind, but the external wind is very narrow, so it's quite hard to see. So in these what we call line profiles, it turns out oxygen 1 isn't that good. But again, if you can then start resolving stuff in space and not just bundling up all the emission together, these position velocity diagrams again just go absolutely bonkers when you have oxygen 1 compared to like a normal Keplerian disk. So this looks very intriguing and maybe useful for identifying evaporation. And the cool thing is it's not using ALMA, it's using something else called the VLT Muse. So you know, that gives us somewhere else that we can apply for to try and, you know, fill in that gap and find evidence for disks evaporating directly in these sort of intermediate UV regimes. I think it's also worth noting just how different career stages work a bit. So as a postdoc, Julia also works on her own stuff. So this is some nice work she's done looking at this is a dynamical simulation of a disk, but it's not just got a planet in it, which is what you can see here. It's got actually a circumbinary disk. So there's two stars, you know, a Tatooine kind of system, right? There's two stars here, and they can actually disrupt the inner disk and cause it to tear away from the main disk and precess at a funny angle. So she's been running these simulations of this sort of situation. And her motivation for doing this was because there's some interesting observations of disks with funny shadows being cast over them. And in these sort of simulations, you can reproduce that. So, you know, you have, if we go back and look at it, in particular in the latter half of the video, as this thing spins around and goes out of the plane of the disk, you know, it casts interesting shadows over the rest of the disk surface. Okay, so normally the light would just be propagating out, but actually what's happening is it's intersecting this inner disk and being blocked out. So that's a really cool project. It's not even fully published yet, but it'll be imminently, I think. So problem number 3, how do stars actually evolve in star-forming clusters? I'm nearly at the end. So Kanar has been doing this for her undergrad third-year project. So essentially, what she's doing is taking a disk that's far away, it'd be boring and looks like this, and then moving it closer to a massive star. And as you do that, eventually it'll start getting irradiated by what we call far ultraviolet radiation. So that is UV light that can't ionize hydrogen, can't strip the electrons off atoms, but if we've got a bunch of molecules, it can break the molecular bonds. And so that warms the disk up and starts driving you a wind. And then as you move the disk closer and closer, you've got this nice atomic wind being driven. And eventually you get to that ionizing radiation that starts to break apart these atoms. And so what Kanar has been doing is looking for the first time at a model that accounts for all of this physics, all of these different processes, at the same time, and looking at how you transition from sort of the one regime to another of being, dominated by molecules being broken up to being dominated by ionization. And this is sort of the main plot she has so far from this work. So this is how much material you would lose in a year as you get closer and closer from right to left to that star. And interestingly, there was a theoretical prediction from the mid-90s that at about here in this particular model, you would go from being dominated by the molecule breaking radiation to being dominated by the ionizing radiation. And in Kanar's work, she's finding that actually that ionizing radiation doesn't really do anything. Okay, even if you add it into and sort of have both types of radiation together, which is what this blue line is, it just doesn't really change the picture very much. And I'm not going to go into the details of why that is, but this is interesting because it tells us, how what's driving the mass loss from disks in different parts of clusters. And then sort of the last shiny project is to do with Lynn, who's the PhD student just starting with me. So she's taking simulations like this one by Ahmad Ali. So this is a star cluster forming from gas, collapsing, like the one we watched near the start. So all of these little points are individual, there's actually small groups of stars, but you can just consider them as individual stars if you want for now. And what she's doing in this calculation is looking at the UV field that all of these stars actually see over time. So, this one's going to see quite a weak radiation field. It's formed far from everything else. This one maybe sees a weak field because it's all over here. And then as they move around, she's sort of recording how strong the UV field is that they're exposed to. And some might be embedded in gas for some time. And so, this is Lynn, who started in January on her PhD. So the x-axis in each of these plots for different stars is time, and the y-axis is how strong the radiation is. And you can see it's not constant with time, which is what we normally assume. It jumps all over the place. It can go up and down. Maybe it passed behind a cloud here and got shielded. Generally, though, as you disperse all that star-forming gas, it is just getting stronger over time. And so what she's doing is feeding this radiation history that the disks will see into disk evolutionary models. And this is like from today, so it's really getting quite rough now, but this is how strong that radiation is over time. And then these plots are comparing what happens if you take sort of our normal models where you just assume the radiation is constant. This is how big is the disk. This is a weak radiation field, intermediate and strong, versus having it evolve over time from the star cluster. And you can see the behavior is really different. And about 10 minutes before this talk, there were some really interesting sort of consequences of this that we were discussing. But you'll have to wait maybe 6 months or something until we've finished the paper on this. So just to summarize what Lynn is doing then, she's actually making this leap from the scales of star-forming regions. She's working out the radiation field that stars see here, feeding that into disk evolution, and eventually, once we've done our first paper looking at how the disks evolve, she'll be working out how that influences the kind of planets you get from these disks. So she's actually joining the dots in this talk of star-forming regions right the way down to planets in her PhD. So this is something I'm really excited about. So the final one, does planet formation care? This is very brief. The main answer is I don't know. This has not been done yet. Lynn hopefully will be able to tell us some more about that in the near future. One thing I will address though quickly is there's been an argument made that because we've got some evidence that planets form really early, so here are some rings in a really young disk, only 500,000 years old, maybe they just form really early, and then when you're evaporating the disk, they don't really care, okay, because they're already just sitting there in the disk and you're just dispersing the stuff around them. Well, last year we found proplyds in a new region called the Flame Nebula, which are sort of 0.2 to 0.5 million years old. So at the very least, they're competing with this sort of timescale. So I don't know if the planet formation does actually care about the disks being evaporated yet, but I don't think we can fully rule it out as being important just because the planets might form early. Right, so 2 more things I want to do. Some take-home messages and then just a quick advert for something. So take-home message number 1, if you're feeling utterly lost, is just planet formation happens in these disks around young stars. Okay. And the second take-home message is that those young stars with their planet-forming disks form in these big groups. And those big groups can affect that planet formation process, either through gravitational interaction or by radiation. And that can limit the mass, the size and the lifetime of disks, which may or may not be important for planet formation. And that links to point 4, which is there's loads to do. And I'm lucky enough that through a whole range of career stages from undergraduate through to postdoc, I've got a lot of good people working on this stuff with me, which is really nice. So just to finish, I want to advertise the course that I lecture. So it's a master's level course called EM Radiation in Astrophysics. And it's looking at things like how we actually use light to work out things like, how do we know that the gas in here is 10,000 Kelvin? How do we know that these bubbles are expanding? So it does that kind of thing. And then how radiation affects dynamics. So again, how star forming regions expand, how disks are evaporated, and how light affects things like the chemistry of gas as well. And I really try and link it to research as much as I possibly can. So if you are doing a master's at Queen Mary, then I definitely suggest that you maybe think about this course. It doesn't have the most exciting title, so I thought I'd just try and mention that it is, in my opinion, a really interesting one. Anyway, I'll go back to the take-home messages, and does anyone have any questions? Do we turn D?
Actually, sir, I have a question.
Yep.
Quickly. It's regarding the formation of the sun, like for our solar system. So, what sort of stellar cluster did the sun form in? Was it a large stellar cluster, a small stellar cluster? And how would that affect like the planets that we have in the solar system right now?
That's a brilliant question and one that is hotly debated. The main reason there's debate about this is due to something called short-lived radionuclides. So these are there's something called aluminium-26, for example, which doesn't survive very long. It decays, and we actually find quite a lot of this in asteroids in the solar system, and the only way you can really produce this is through a supernova. So for a long time there's been a debate about whether or not the star had to form in our sun had to form in a big cluster, because that's actually in these clusters that you have your supernova go off. I actually have an extra little slide on this. So this is a massive star will die after about 5 million years, and when it does, it explodes. So here's an explosion going off in one of these star clusters in a simulation. And when it does that, it launches these sort of short-lived radionuclides everywhere. And so people, have been saying, well, the sun must have formed in this kind of environment because it's got quite a lot of this stuff. But in recent years, there's been a lot of work saying that actually if you look at a bigger fraction of a galaxy, you can actually maintain quite a lot of that just because supernovae are going off all the time everywhere pretty much. So, it's still hotly debated. Unknown, I think.
That's fine. Thank you so much. Does anybody else have any questions for Dr. Thomas before we wrap this up?
Yeah, hi. Earlier you mentioned that we couldn't observe certain types of planets because of their orbits and their mass.
Mm-hmm.
What technological advances would need to be made before we can start looking at these?
Yeah, I mean, that's a super question. So, and I don't necessarily have the best answer for this. So over here, it's just that, it depends on your method. So normally we're trying to find planets either through the radial velocity method. So that's where the planet makes the star wobble, just through the gravitational interaction. And the other one is transit. So that's the planet passes in front of the star. So if the planet's really far away, which is what you have on the right of this plot, then its gravitational pull is very weak on the star, so it's hard to see that way. And also its year is very long, so your probability of it coming in between you and the star is very low. Okay, because you have to look for a very long time to see that. So that's what explains over here. It's probably more just that we need to look for longer. But then getting down to low planet masses, there again, both ways, you've just got to improve your sensitivity. So if you have a low mass planet quite far away from a star, it's not making it wobble much gravitationally, and it's also causing only a small dip in the brightness when you have a transit. So yeah, out here it's look longer, and in here it's build more sensitive instruments, I think is broadly the answer.
Thank you.
Professor, you have a question in the chat. I'll read it out for you. It's from Susanna, so your student who you worked with. She says, I have a question too. What are you most excited about in terms of future research on planet formation and any huge and exciting international projects?
Crikey, that's a big question. Yeah, I think of the stuff that I've mentioned, I'm very excited about Lynn's project, just because, it's the first one sort of that's going to make this link from the large scales down to the planets directly. Crikey. There's just so much going on. It's hard to, across what everyone's doing. There's a lot of exciting stuff at the minute about actually trying to find the planets within the disks. So, I mentioned these rings. If these are planets causing these features, then surely we should be able to go and look for the planets. So that's quite exciting, trying to actually spot the planets in the process of being produced in these things. And then the other part was about the biggest, what was the second bit about international collaboration, was it?
Yeah, so any huge projects, international projects that you are looking forward to or that you can tell us about?
Well, I mean, again, there's so many big instruments coming up. There's the Square Kilometre Array, which is mostly going to be used for cosmology, but actually can do things like look at larger dust grains in these disks, which are sort of the next building block up towards planets. So yeah, there's other very big telescopes. There's the James Webb Space Telescope coming out, which again will provide a new exciting look at these disks. Again, just linking to what I'm personally working on, this Hyperion thing, if it gets accepted, will be really exciting. I'm mostly a theorist. So the idea of working on a space telescope is really exciting. But this isn't a Hubble or a James Webb Space Telescope type instrument. It's sort of a much smaller thing, but it's been quite cool to work on.
That is amazing, and we're all looking forward to the new telescopes coming out, so we all have a chance to learn more about the universe that we live in. Any other questions from anybody before we wrap stuff up? Dr. Susanna saying thank you. Well, Dr. Thomas, Haworth, I just want to say thank you so much on behalf of all of us. I'd like to say thank you so much for this amazing presentation. I learned a lot today, and I bet the others learned a lot as well. Before we do finish this off, though, I wanted to say again that this was a collaboration between the IOP, which is the Institute of Physics, and CISA. And I think there's another message in the chat. Let me just check. Oh, yeah. Luke is saying thank you to you. So yeah, it's from the IOP and CISA. I did mention that there was a prize available today. It is a £15 Uber Eats voucher, and I put everybody's name in a random name generator, and the name that came out was Enzo Olivieri. I'm hoping I'm pronouncing that right. So Enzo, if you are here, congratulations. You won a £15 Uber Eats voucher. To claim it, if you could just put your email down below in the chat so I can email you personally with the voucher. So congratulations for that. before we do go, I will ask for Shay or Luke to tell us about any upcoming projects, any upcoming events that are happening with SciStar.
Yeah, brilliant.
Yeah, of course. You want to go for it, Luke?
I'll go first, and if I miss anything, you can say. So thank you firstly to Dr. Thomas for once again giving us a great talk. We had one over the summer, and this was very nice, very different, so I enjoyed the difference. Events we've got in the future. Okay, next week we have Dr. Timothy Clifton. He'll be talking about cosmology. I'm not sure what yet, but he's big into black holes. So if you love black holes, this is the place to be.
Black holes, wormholes, and large-scale structure of space-time.
The whole shebang. And then the week after that, we have a PhD talk with Beltran, who was an ex-member of the committee. I noticed we have several ex-committee members here as well. Azib is in the chat, the ex-president. And various other people. He'll be there, PhD students as well. And then finally, just booked on the 21st of April, an unknown time at the moment, we will have Professor Thomas Bohr, grandson of Niels Bohr, will be talking about his grandfather and also about his research into fluid dynamics and chaos theory. So hopefully, he'll be calling in from Denmark, hopefully, so it won't go wrong.
That's a great event.
Look forward to. I'd also point out we've also got Dr. Chris White is doing a talk on the 7th of April about the double copying theory. But that's a little bit down the road. That's before the Thomas Bohr. But yeah, so
there's a poster. You can see the poster. Anyway,
yes.
Lovely. Thank you for your talk. Thank you to Neeshay for sorting this out with the IOP. People should go and sign up for the IOP because it's a good deal, especially when you're a student. People should also go and sign up for the SciStar membership because it's a good deal when you're a student.
Regarding the Institute of Physics, so everybody, if you have any questions about the Institute of Physics, please go and search on their website. If not, you can email me. I'm also on the SciStar group chat if you're already a part of that. So just tag me, just ask me a question, and I'll be really, really happy to answer any questions you have. It's a great opportunity for you to learn more about the amazing research that is happening in the physics community right now. So yeah, so thank you so much, Dr. Thomas, again. It was really, really great to have you here today. Thank you so much to everybody else, and we hope to see you in the future events.
Thank you very much. Bye, everyone.
Bye, everyone. Hopefully see you next week.
Yeah.